The next talk will be by Peter Sanciolo from Victoria University, and he'll walk you through the project that he's finished up on removal of silica to enhance the recovery for reverse osmosis and waste brine volume reduction. Peter?
Thank you, David. So the project, although the title says removal of silica, there are other approaches that you can take to mitigate silica scaling, and I'll talk about that as well during the presentation. The participants, people and organisations, we have Victoria University, and there's myself, Nicholas Milne, and Stephen Gray from Victoria University. We've got from Origin Energy, Eddie Ostasevich, Mark Baton, and Greg Perrell. We had some input from Hatch, Kelvin Taylor, and Mark Mullett in conjunction with Minara Resources, who provided the samples. And then we also had input from University of Texas, El Paso, Anthony Tarquin and Thomas Davis. One of the first things we did, as is often the case in research projects, is to do a literature review to see what the knowledge gaps are within which you can make the most difference with your research. And that'll be written up as a journal article very soon, and that's one of our commitments to spread the word of what we've done with our research. But that knowledge also gave us the enough information to structure a PhD project, and that's been initiated at the moment, and that will look into the silica chemistry, and that there's a lot that's not known about silica chemistry that, if we did know, would improve our chances of solving the problem. We worked with waters from Origin and Minara Resources operations. The Origin water was a coal seam gas water, so it's the water it's a byproduct of gas production. And the Minara Resources water was the groundwater that they used in their process. They don't have access to any other type of water, so they use groundwater. We looked at two different ways of approaching the problem. One is to remove the silica, as the title of this talk states. And we did that, we only did that option for the Origin water because it had it was buffered to a very high degree, so we couldn't really change the pH to try a low pH RO. But we did try that other approach of using low pH RO with the Minara water, which had a less buffering capacity. The outcomes of this research so far have been that Origin is really quite keen to have a further look at the adsorption, removal of silica by adsorption, and they're doing that on a larger scale. The low pH RO option, we've shown that it works, and we've given some indicative funding for or costs for it. But at this stage, it seems to be it's just an option that may be used in the future if economic climate changes and if water scarcity increases. We carried out a preliminary costing of the options for the mining water, and I'll be showing some results there. And finally, our last commitment was to carry out to participate in a workshop to show our results to the general community. As an introduction, I put up a graph here of the expected silica concentration as a function of water recovery for a water that has 74 milligrams per litre silica. And there you have two curves there. The blue one is the silica concentration that would occur if no scaling occurs, and the red one is actually the actual concentration of silica, soluble silica, that occurs if silica scale starts to happen. You can see in this curve you have consecutive doubling of the concentration as you go from 50 to 75, and then doubling again to 87.5. So that by the time you get to about 94%, its concentration would be 16 times the original concentration. But as I said, we get silica scale formation, and to avoid that, you have to run the RO process at a water recovery that is below that threshold. So with this one would be roughly 60%. Now, this limit here that I've put in as 200 milligrams per litre for silica is very dependent on the actual water composition. It's very different to the type of calculations that you can do for salts, for example, that you know the solubility quite accurately. For silica, it's very, very dependent on the composition of the water. And there I've shown, I think these graphs have moved a bit, but really this slide is supposed to show that there are different factors that must be considered when you're thinking about the solubility of silica. Firstly, there's silica's behavior in water, simply the reaction of water with SiO2, forming silicic acid. And that's quite a simple system, and you know that the concentration, the solubility will increase with increase in temperature, according to that, to a relationship that's been found empirically. There are, however, other factors which are important, and pH is really the greatest. What you have is silicic acid acting as an acid, as the name suggests, and these are the acidity constants shown there at 25 degrees. Now you can see the first reaction has an acidity constant of 10 to the negative 9.8, indicating that at pH 9.8 there's roughly equal quantities of the anionic species and the non-ionic species. If you increase the pH even further to 12, you get the production of the divalent ion as more acid comes off, more protons are released. What that's supposed to show at the bottom of the slide there is that these silicate ions can react with any metal ions that are present in solution. So calcium and magnesium can interact with them and form insoluble precipitates, which can be the fouling species in the RO process. And lastly, there's also polymerization of silica, which can occur and has its own kinetics, which are dependent on pH as well. And that's shown in this graph over here, and you can see that it's very, the polymerization is quite slow at low pH. It's fastest in the region between 6.5 and 8.5, and then it goes slow again. The reason for that is probably that some of the silicic acid is being changed to silicate ion, so there's a lower concentration, and that's but Nick will be talking about the chemistry in a little more detail later on, so you'll see the proper equations there in Nick's presentation. So in looking at the literature, we found two real ways of approaching the problem. One is to remove the silica, and one is to operate the RO under conditions where the silica is of a higher solubility, so it doesn't precipitate. Looking at the removal, there's a whole host of ways you can remove it. As I mentioned earlier, you can add calcium and magnesium under alkaline conditions, and that'll form the calcium-magnesium precipitate or silicate. You can add other ions such as iron 3 or aluminium. You can generate the ions in solution by electrolysis, electrolytic sacrificial electrode. Or you can do a whole host of adsorption studies, or adsorption ways of absorbing it, using different adsorbents such as hydroxides or some naturally occurring minerals such as goethite, gibbsite, and alumina. Another way is also seeded precipitation, If your solution is super saturated with respect to silica, if you add a seed of silica, you can induce that precipitation to take place. But that's only to the solubility limit of the silica. And finally, you've got ion exchange, which you can do. It's, if your silica is in the ionic form, you can absorb it or remove it onto ion exchange. Regarding the second option, which is working with the RO, not removing the silica, but just using the RO under conditions where the silica solubility is higher, you can work at alkaline pHs, but you've got to remove the calcium and magnesium first, otherwise you form calcium and magnesium silicates. And that's essentially the HERO process. The other alternative is to go to the other end of the pH scale and work at low pH. And that's what we tried in some of our studies. So one of the waters that we started to work with was the coal seam gas water. Now, in the process of removing, extracting gas, you've got to extract an overlying layer of water, and that water contains a lot of salt. And the volume that you have to extract to remove the gas is really quite considerable. It's estimated to be 150 gigalitres per year for the Queensland Basin. Origin has the capacity to treat 32 megalitres per day in its current operations. Now, the water is so salty that RO is used to treat it, but they can only go to a solubility, to a water recovery of about 80%. After that, you start to get scaling. So they would love to be able to decrease the volume of waste, that 20%, down to something more manageable that can be used in evaporation, or even to extract some of the valuable salts. I think that contains a high concentration of carbonate or bicarbonate, so you might be able to extract those. So you could reduce the volume to about a quarter. Another benefit is also not only in the volume reduction, but also what you do with the water that's produced. You can actually make the area where you're doing your gas mining a very productive area by using the water for irrigation. There I've shown a couple of graphs of, what I've done is worked out, I've shown you an example of what happens if you're working at 80% water recovery with a volume of about 11,700 megalitres per year. Since you're at 80%, you only produce about 9,300 megalitres per year of irrigation water. And that will allow you to irrigate about 1,600 hectares. The brine that's produced is 20% of the original figure, so about 2,300, and you would need an irrigation, an evaporation area that's about 230 hectares. So if you do a ratio of the two, you see that you're able to irrigate only 7 times more than you have to take up by building evaporation ponds. I've actually done that calculation for higher water recoveries, and the graphs down the bottom show the results there. They've been corrupted a bit in loading them onto the presentation here, but I think you can see you have a linear increase in amount of area that you can irrigate. It's quite considerable, from about 1,500 to about 1,900, so that's quite considerable. The pond area that you need, again, is linear, but it gets down to very low values. This point here is about 30 hectares. If you do the ratio of the two, you'll see the real benefit of what's happening here. If you can work at high water recoveries, say 95 or 96, you can achieve ratios that are very high. So something like 30 or 40 times more than the area that you use for evaporation ponds, you can use for irrigation. And that's when it starts to become a real valuable prospect. The RO concentrate that we used, we of course analysed it initially just to see what sort of things are in there. Things to note here that calcium and magnesium is quite low in these waters. Another thing is the organic carbon is quite high. So it's a coal seam gas water. It's not surprising that some organics have gotten incorporated into that water. Another thing about this brine also is that it's very highly carbonated, as I mentioned earlier, and so we were restricted to procedures that don't change the pH. So the low pH RO was ruled out, and also changing the pH to get better adsorption perhaps was also out of the question. So we worked at the native pH of 9.3. We chose from the literature a number of promising adsorbents. Activated alumina was found in the literature to be quite promising. We chose two different activated aluminas. Here we chose to use ones of different size, particle size. We also had a look at the silica removal using a resin, just an ion exchange resin, and also a silica gel of various pore size, a couple of pore sizes. And what we also did it was to see whether pretreatment improves the adsorption using these adsorbents. So pretreatment using ion exchange to remove the hardness, or using activated carbon to remove the organics. There's a result of the ion exchange pretreatment, if you like, just to show you that it's doing something. It's actually reduced the calcium and magnesium quite well for this sample from site 1. For this sample, we still have residual quantities of calcium and magnesium. But we then took these treated samples and put them through the process, absorption process, using different aluminas. Now here you see in the left of the graph what I've called activated alumina 1, and it's basically of different particle sizes. And it's not surprising that the lower particle size works best because of the higher surface area. There we have the result for ion exchange. That's an ion exchange process for removing silica. There we have the results for another activated alumina, and then the silica gel. And you can compare those to the initial water, raw water concentration, and the softened water concentration. And you can see, obviously, these ones are the best out of this lot. And interestingly, some of them are even higher than the initial quantities of silica. And that's basically because these are silica gels and they're dissolving in the water and making the thing worse. Next slide just shows another sample, similar type of thing, different values, but still this lower end adsorbents seem to be the best. Next we had a look at activated carbon as a pretreatment to remove the organics. And we did a UV spectroscopy on the sample before and after this AC treatment to see what's being removed. And you can see that activated carbon is able to remove some of the components but not others. For these 220 nanometers for compounds that absorb UV at that lower wavelength. For this high wavelength, there's quite a lot, almost total removal of the carbon. We also found there was considerable difference in the organic carbon content of the samples, even from the same site. These are two samples from at different times, and you can see quite different peaks being there, different quantities. Some peaks are not there initially, but they are after. So quite a lot of variability there. These are the results for activated carbon treated waters, just to see if it makes any difference. There's a different sample, so the raw water values are different to the earlier graph. But you can see definitely that activated carbon treatment doesn't improve the adsorption at all. In fact, it seems to be making it worse. How that is, we don't know. The fact that they're all higher makes you think that it's not just experimental variability, but there's something going on there. So to sum up this section, removal of calcium, magnesium and organics does not improve silica removal by adsorption, and activated alumina is able to actually reduce the value down to a lower value. We next went and picked out 3 of the activated aluminas that we trialed and did some further work to try to optimize the conditions a little bit. Here we show the effect of temperature. You can see for the 2 samples they both have this curious hump at about 25 degrees. And what we believe is going on there is that we have two things going on. We have an increase in absorption capacity of your alumina at a higher temperature, but also increased solubility. And I think it so happens that the solubility wins out over the increased absorption at 25 degrees. But you can see that a higher temperature is actually quite a good thing to do. The best results are achieved at that higher temperature. This is adsorbent dose, and you can see the 2 samples needed different quantities of adsorbent. So really tells you that you really have to do this sort of work to determine the optimum conditions for each specific site that you're going to be treating. So to sum up this section, we know that silica removal by adsorption onto activated alumina is favoured by high temperature and high adsorbent dose. We know that we're able to get to about 45 milligrams per litre of residual silica using adsorption. And given that the initial RO concentrate was at 80%, the curve shows us that we reached this 200 milligram per litre limit at about 80%. So we need to keep the water recovery below that for this RO treatment. So overall it ends up being about 96% water recovery. So that's very promising. The next slide shows really what I was talking about before about the ratio of amount of area that you devote to evaporation compared to amount of area that you actually use the water for a useful purpose. So that's that graph put up again, and just to give you a visual image of what's really happening, this is for 1/7 of the irrigation area at 80% water recovery. You can use evaporation ponds that are 40 times smaller than the area that you irrigate. And then I think you can see that it's a much more viable process, prospective, to actually use this scenario rather than this in terms of practicality of handling all this enormous amount of brine. We also had a look at regeneration of the activated alumina. So you can absorb the silica onto it, but can you reuse it? So these experiments were performed to see if we can get the silica off the adsorbent and then use it again. And these are some of the results. You can see that we did a number of steps of sodium hydroxide treatment at 25 degrees on this activated alumina, and you can see that the silica concentration is quite high. It's coming off the adsorbent, but we also have quite a lot of aluminium being liberated as well. So the alumina is, we know it's a little bit soluble at alkaline pHs. and that's something that will have to be considered, that you're going to lose some of your absorbent if you use if you use caustic as a regenerant. So that's just reprocessing of that data. The silica desorbed as a percentage of what's being loaded on top on the silica, and you can see you'd need about 10 steps to reach about 80 or so. So 10 rinses, if you like, with sodium hydroxide. And that's the adsorbent lost, the amount of alumina that's being lost. So it's quite considerable. If you take the average of those three, it ends up being about 5 or 6. That slide's just basically a reiteration of that earlier slide. So to sum that up, regeneration of activated alumina is possible using 2% sodium hydroxide. The silica loading rate of the regenerated adsorbent is still good after 3 absorption, desorption trials, so that was good. But we had approximately 6% loss of alumina with each regeneration. So that's something to bear in mind. And you'd certainly want to optimize that on a larger scale. This is just lab experiments in small beakers. Going on to the Minara Resources water. Now this was a groundwater used by the company. It's actually a nickel mine, and it uses quite a large amount of groundwater, about 26 megalitres per day. And this has to be desalted because the salts interfere with the process of mineral extraction, and also the salts corrode the process equipment. So what Minara does is they do a RO on it, but they can only achieve about 60% water recovery before silica starts to be a problem. So if they could achieve 95%, that would be an enormous benefit to them. You'd get about 1/8 of the volume of waste from the process, and 1.6 times as much usable water out of the water that you extract from the ground. So for the Minara Resources RO concentrate studies, we had a look at a couple of things. We had a look at low pH RO, and we had a look at silica removal in the same way as we did for the origin waters. For the RO studies, we had a look at permeate flux. We had a look at the silica, calcium, and magnesium concentration on the membrane, and we also had a look at the membrane with the SEM, and did some elemental analysis, and we did some IR on it to try to characterize what the species that are being moved or are fouling the membrane. That's one of our analyses of the RO concentrate that we received. Thing I want you to notice here is we have very high quantities of calcium and magnesium in this water, 10 times more than the earlier water we looked at. Another thing to note is this low alkalinity, and that allows us to actually adjust the pH and gives us a lot more room to play to find the right conditions. The equipment we use to study the scaling is this flat sheet apparatus, in which we have a membrane about the size, about 100, 114, I think it is, square centimetres, put into a flat sheet module, and what you do is put your water in a reservoir and you pump it to the flat sheet, and you bake your concentrate and return it back to your feed container. And the permeate that comes out is collected and weighed on a balance. So with time you get more and more water here, you get less and less water here, but it's much more concentrated as time goes by. These are the results for a couple of our early tests. Now here I've plotted the flux compared to the initial flux on that graph as a function of water recovery. And you can see that the low pH runs seem to be overlapping here, whereas the native pH run is a little bit further away from the others. You can also see quite a lot of fluctuations in the flux. That's just a characteristic of the equipment. It fluctuates. But on the basis of that, you really can't say much because of that high variability. So we had to repeat these tests a number of times to see if we could get better agreement of the results. And this is a result, all the results put onto a graph. It's quite messy and looks nice, it's colorful. But if we zoom in on this section here, you can see what's going on a little bit better. The low pH runs were able to maintain a higher flux for longer, or higher water recoveries, than the native pH runs. And you can see that having anti-scalant, the blue is with anti-scalant, the red is without, and you can see that there's quite a good agreement of the results. Low pH, the anti-scalant doesn't seem to be making any difference there, whereas we get quite a lot of flux decline with the native pH runs. During those experiments, we took samples with different water recoveries as time went by, and here we have the results of the silica concentration, and you can see the open squares or open symbols are for the native pH, so the higher pH. The solid samples, the solid symbols are for the low pH runs. And you can see that the silica is essentially dropping out for the high water recovery values for high pH. Whereas in the low pH, it's maintaining itself close to the theoretical no scaling curve. If you have a look at calcium, we don't get that effect. The open symbols here are not lower than the actual predicting curve, telling us that really there's no calcium or magnesium, or very little calcium magnesium that is removed. There's the curve for magnesium. What we did with the membranes at the end of those runs was we put them through FTIR, and these are a few of those results. In grey here we have the unused membrane. You can see it has its own characteristic peaks. The pH 3 curve showed us a little bit of difference in some peaks here. These peaks are probably bending vibrations of silicon and oxygen bonds. This one we're not quite sure about, but you can see with the high pH run, we also have these another peak here. So perhaps silica oxygen stretch there. That's probably an artifact. It's often seen due to CO2 absorption, so it could be that someone breathed on the membrane after collection. So, so that tells us there's something to do with silica perhaps happening there in this membrane at high pH. When you have a look at them under ACM, you can see the unused membrane. It's really quite clear. There's no particulates there. This is all the material that the membrane is made of. At high pH, the high pH run, you can see lots of scaling there, as you'd expect, enormous amounts of scale that's obstructing the view of the membrane completely. And then finally, if you have a look at the low pH membrane, you can see that it's roughly, a lot of it's similar to the original, but there's some what look like to be scale particles there. Now that's not a representative sample, so you can't really say how much from that, but you can say that it probably started at scale at that at the end of that run. Elemental analysis we did on those membranes. You can see the unused membrane looks like that. You can see these characteristic peaks. That's sulfur, probably due to the membrane materials on sulfone. What we see for the native pH, you see the appearance of a lot of other peaks. Silicon. And there's also oxygen that is at 0.5, which is quite a lot higher than in the original. For the low pH membrane, you can see the spectrum really looks quite similar to the unused membrane. So really indicating that there's not much deposit of material on that membrane. So low pH RO scaling study, we know that operating at pH 3 minimizes silica scale formation. We know that from the higher soluble silica at high recoveries at that pH, and we know that from the high permeate flux or higher permeate flux. And we can estimate from the 85% water recovery that we went up to that we could achieve about 94% with very little scale formation. The FTIR data tells us something was probably that we already knew, that there's silica there and it's possibly carbonate. The SEM images confirmed that the flux decrease at native pH is due to scaling. You can see that scale there quite obviously. And low pH operation minimizes that scale formation. And again, EDX, the elemental analysis, tells us that native pH conditions, silicon, calcium, and magnesium, and oxygen are present. So that's the low pH RO. We also did adsorption studies on this other water, similarly to the origin water. Here we see the effect of pH with a select number of different adsorbents. And you can see that with no adsorbent, the curve looks quite like that and actually decreases on its own without any adsorbent being present if you have a high enough pH. Adding the adsorbent makes a little bit of a difference, and that the greatest difference is made at about the native pH of the water, which is 8.6 in this case. And that is with activated alumina of very fine particle size. If you have a look at the calcium concentration, it does a similar thing, and magnesium. We also had a look at the adsorbent dose at different temperatures, and you can see, again, as we saw earlier, that more absorption at higher temperatures, and obviously, if you have more adsorbent there, you'll get more removal. But the quantity there is quite enormous compared to the other sample. The other sample we're using 1 or 2 grams per litre. This is at 10 grams per litre. So it's going to be a much more expensive process for this water. I'm sorry about that quality of that. It's moved again. But you can see you can achieve quite low silica concentrations if you have high doses of adsorbent and quite a high temperature. So that value is about 16. If we put that value as a starting concentration in our modelling, we can see we can go all the way up to 90 before we reach that 160 ppm silica formation threshold that we saw. So again, we can do, we have initial concentration is 60, initial water recovery that the company carries out is 60. We carried out RO on that, and we got 90%. So 90% of that 40% gives us a total of 96%. We also did some very rough not modelling, but cost analysis of the different options. The options we had a look at was low pH RO and batch mode. We looked at just precipitation without any adsorbent, but with the sedimentation stage to obviously remove that silica. And then we looked at 2 different temperatures for removal of the silica using an adsorbent. So you can see that the low pH alternative is really the most economically favourable, if you like, has the a pretty low capital expenditure and very low operating expenditure. Precipitation is quite expensive, and that's mainly due to that sedimentation stage that you need, that needs enormous tanks, sedimentation tanks to remove the removed silica. Operating expense is a little bit higher. When you look at the alumina options at ambient temperatures, obviously you'd need more alumina if you're working at ambient temperatures than at higher temperatures. So there's a saving in the capital expenditure because you've got smaller equipment, because the equipment works, you can achieve the same value with less alumina. The operating expenses there, since the heat to heat up the alumina is waste heat from the company, it doesn't really contribute very much to the operating expenses. And the extra alumina really doesn't make much of a difference either, because you still have to clean it and carry out all the procedures that you do with a lower amount. So, final conclusion, coal seam gas. High buffering capacity prevented other investigations, so we only looked at adsorption. You can remove silica, and we can estimate that 96% water recovery might be achievable. And you can also regenerate the adsorbent using caustic, but you've got to keep in mind that you've got quite a considerable loss of alumina, and you really need to further optimize it on a larger scale to see what's going on there. For groundwater from the mining operation, we had a look at both alternatives, low pH RO and silica removal by adsorption, and also had a look at precipitation as well. We estimate from the low pH RO that you might be able to achieve about 94% water recovery on that, using that. So obviously you'd use batch mode. With the adsorption, you can estimate to achieve 96% water recovery. And preliminary costing, very rough costings, really tell us that low pH RO might be a better alternative than the other ones for this water because of the high expense of a large amount of adsorbent required for this water. So with that, I thank you and ask you if you have any questions.
Thank you, Peter. Questions from the audience? Yes.
With the pH RO drilling down into your OPEX there of $80 a bead or 8 cents a kilometre, does that take into consideration the buffering to pH in a range that would be acceptable for 6.5 to 8.5, or is it simply just being able to produce the permeate? And just second to that, if it does, what impact on the salinity of the permeate does that have to buffer it up?
Yes, the question was, do you need to, does the costing include pH adjustment back up to a neutral pH for use of the water? But I think they're able to use the water at very low pH in the mine, so they don't need to bring the pH back up again. So it's not a cost. It's actually good because you're using acid anyway to lower the pH.
So you're going to
Exactly. Yes.
Okay. Question?
In terms of the operating costs, as you put up, I guess I just need some clarity. Are we talking about water from a tailings pond, which is aerated, or is it direct from the extraction process? So it's an anaerobic environment. We're talking, what sort of environments are we talking about operating these processes?
Well, we're talking about groundwater and treating the water that's been run through an RO process directly.
Right, so you're maintaining anoxic emissions during the RO treatment stage.
Yes. What's the point there? Sorry.
Just wondering whether or not there will be benefits that were extracted from those depths would be higher in temperature, and whether that would have an impact on the operating expenditure rather than allowing for that water to cool and then bringing it back up to temperature again.
Yes, the process. If the process uses a higher temperature, we only investigated it at 20 degrees or in the lab.
Yeah.
So I don't know what would happen with a higher temperature. If the source water is at a higher temperature, what would happen? We would probably start to scale earlier. And so instead of being able to achieve 60% in your first run, you probably achieve less.
I've got a second question also of interest. The absorption, the percent reduction through absorption, it did show that with increasing temperature you were able to achieve a higher removal, slightly higher. I just wonder, could you take us through what process of selection for the activated carbon was used? Was it a coal or was it a coconut?
It was
the activated carbon.
Yeah, the question was what activated carbon we used for the decrease of the organics, and the answer to that is was coconut shell. It's actually on the slide, I think, at the bottom. But it was arbitrary, really. We just wanted to see whether it would have an effect, and if it did decrease these organics, whether it made a difference to the adsorption process with activated alumina. So it wasn't supposed to be, an optimized process as such.
Okay. Anna, did you have a question?
Yeah, I just had a question to follow on from that. Did you actually measure the concentration of organic carbon that was removed? You showed up there some plots from size exclusion chromatography, which really doesn't see all of the activated carbon, doesn't see all of the dissolved organic carbon or the total organic carbon. Did you measure the total organic carbon at all?
To tell you the truth, I really don't know. Nick, do you remember whether we actually measured a value for the activated, for the treated water in terms of organic carbon?
I know we saw some removal, but I can't remember how much.
Okay, that's the point. Yes.
Does the organic carbon interfere very much in the silica removal process at all?
Well, according to the results that we saw, it didn't really make much of a difference. But we did notice quite a difference in samples. Some would come back with a definite odor and some color, whereas others might be have less odor and different color. So
yeah, it might be interesting to get some more characterization of that organic matter and to see what the variability is in the actual character of the organic matter over time, and try and understand a little bit about how it varies and whether the variation would affect your treatment process.
Yes. Well, that may well come into the realms of the new PhD that we're doing in silica chemistry. We'll be looking at real waters, and so if organic carbon is a major component that influences silica precipitation, then it'll come up in that. But this really, I should have added that this project was only supposed to be a 6-month project, and it went to 12 months. So it really just touches on a lot of issues that really need to be looked at in much more detail.
Okay.
You may have just answered my question.
in the timeline that you suggested. How did you land on activated alumina being the sorbent of choice as opposed to an iron?
Well, it came up in the literature as quite a promising adsorbent to use.
So it's not as that you have a source immediately of activated alumina, as opposed to something else. It's just that was played with.
That was indicated by the literature. I mean, the literature also said that sometimes silica gel works and ion exchange works. So it's just a matter of sourcing some activated alumina and trying it out.
That's something I'll discuss a little bit more in my talk. So that'll come up a bit more in the next one.
Okay. Any other questions? Frank?
I have 3 different ones. I asked one at the moment. Was the high pH process discarded because of patent on Hero? Or was it no application for those particular cases?
I'm going to repeat that.
So the high pH, the question was the high pH alternative for RO discarded because
of patent
issues?
Hero.
No, we didn't really look at that. I think it's just that it's being done, and really, in the brief time that we had, we thought there was a lot more promise in going to the lower pH RO work of Tony Tarquin, University of Texas, El Paso. We saw some very promising results, and we wanted to try that, simply because it's something new.
Does it consider also impact of long-term low pH on the membrane itself, on salt rejection and life of the membrane? Is this also part of this project?
It's not part of the project. The project is now finished, but it may well come up as an issue in the PhD if we find that we get change in membrane characteristics with time, or pH, if you like.
Last of those standard questions, what did you use, what muscle did you use to bring to pH 3 from?
We used sulfuric. Yeah.
This issue of pH raises a question in my mind. Are there certain membranes that are more suitable for low pH application than others? And if so, how would you get a guidance on that?
We didn't look at that at all. The membranes we used were seawater reverse osmosis membranes, simply because of the high salt content of these brines. That's something for further investigation, certainly.
I have a question from someone online for you, Peter. They want to know whether any other pre-treatment options, any other pre-treatments were considered, like MIEX to remove organics, and its influence in the next steps to remove silica.
You have to repeat that.
We want to know whether
any
there are other treatment options,
pre-treatment
options, such as
MIEX?
MIEX?
Yeah, to remove organics.
No, we didn't consider any of that. Nick, do you know of anything?
Effectively, what it came down to at the time was that the organic content of the water was actually supposed to be very low. When we received the water, it had a significant organic content. So what it all came down to was there's a theory out there that there's silica involvement with organics that could actually prevent the adsorption process occurring. So we were looking to see if we could just find a way to remove some organics to look at the impact of that. And that's what those results presented were all about. Now you're probably going to have to repeat that to people.
I've got the room mic on, and hopefully they picked it up.
Oh, yes, good.
Thank you.
All right, any other questions? Okay, well, thank you, Peter. Thank you for a fine presentation.